Part 2 of Unit 4 is about enthalpy and calorimetry. The definition of enthalpy is for a system at constant pressure, the change in enthalpy is the heat that is gained or lost. We're going to abbreviate enthalpy with the letter H because that makes lots of sense, but that's the way it is. And when we're doing calculations with enthalpy, we're trying to find delta H, the change in enthalpy or the change in heat that's gained or lost by a reaction. Our equation for calculating the enthalpy of reaction, it's this right here, delta H. It's equal to the sum of the enthalpy of the products minus the sum, that was ugly, of the enthalpy of the reactants. You just need to remember products minus reactants. You're going to add up the given enthalpy terms of all the products in a chemical equation and subtract the total of all the reactants. If you do this equation and you come up with delta H being a positive number, that's an endothermic reaction. And in an endothermic reaction, that means that the system absorbed heat. It absorbed energy from the surroundings. If delta H is a negative number, that's an exothermic system. Exothermic means the system gave heat or gave energy to the surroundings. So something like a fire is exothermic because the system is giving off heat that you feel. And a reaction that causes something to feel cold would be endothermic. That system is absorbing the energy from the surroundings, making the surroundings colder. One thing we need to remember when we're thinking about enthalpy, when bonds are broken, that's an endothermic change. For those bonds to break, that molecule has to absorb energy to break that bond. So breaking bonds is endothermic. When new bonds are formed, energy is given off. So forming new bonds is exothermic. Go ahead and write that on here. So endothermic is breaking bonds, and when new bonds are formed, that's exothermic. Another thing we need to talk about this unit is calorimetry. Before we get into the details of calorimetry, we need to define a couple terms. The first one is heat capacity, and that's just abbreviated with capital C. Heat capacity is calculated as heat absorbed divided by the increase in temperature. So the higher value of C we have, the less change in temperature something's going to experience from absorbing the same amount of heat. Think about your car sitting outside in the sun in the summer. And if you've ever burned your hand on the metal part of the seatbelt, this should be pretty familiar to you. The fabric part of your seatbelt and the metal clip are going to have different values of C, different heat capacities because they're different substances. The value of C for the fabric is going to be higher than the value of C for the metal clip. The metal clip is the part that gets real hot and burns you. Even though they're absorbing the same amount of heat, the fabric strap and the metal clip, the clip is going to feel hotter, so it's going to have a lower value of C, the heat capacity, than the fabric strap is going to. Another term we need to define is specific heat capacity. It's abbreviated with the lowercase s. This is defined as the amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree. And the main difference between these is S is for a specified amount of a substance. Heat capacity is just general based on what the substance is, but in specific heat capacity we're talking about 1 gram of something by 1 degree. The units for S are joules divided by degrees Celsius times grams. This is a picture of a simple calorimeter. This is what we use to perform calorimetry in. Calorimetry is just about tracking the heat change in reactions. So we've got two coffee cups sitting inside each other with an insulated cover over it with a thermometer and a stirrer. This creates a very closed system for a reaction to take place in so that there's very little energy loss. So in the reactions, what we're measuring is the energy change to the surroundings. All these reactions are taking place in solution, which means they're dissolved in water. The system is going to be the molecules doing the reaction, but we're actually measuring the surroundings, the water around them. So we're measuring the amount of heat that's transferred to the water around the molecules that we're trying to find the change for. Our important equation for calorimetry, it's pretty easy. It's lowercase q, that's heat, is equal to ms delta T. M is mass in grams, so the mass in grams of the total mass of whatever solutions or substances you're dealing with. S is the specific heat. And delta T is the change in temperature. When you plug those values into this equation, you'll find you'll solve for Q, which is going to be a value given in joules because we had joules as part of our specific heat term. One other thing that's real important to remember, and it's the reason why I introduced enthalpy first, we need to remember that Q is actually equal to delta H. When you're measuring the enthalpy, you're just measuring the heat change in a reaction. That's what we calculate with this calorimetry equation. So the heat gained or lost in a reaction is going to be abbreviated with delta H or Q, just depending on which reaction or which equation you use to get there. So let's look at this example using our calorimetry equation. Barium nitrate and sodium sulfate solutions with a total mass of 2 kilograms react, causing a white precipitate to form, and the temperature of the solutions to go from 25 Celsius to 53.1 Celsius. Calculate the enthalpy change for the reaction. The specific heat of water is 4.19 joules divided by Celsius times grams. So we're going to be using Q equals ms delta T. Solving for Q, they told us what the mass was. It's 2 kilograms. We need to put that in grams. So it's 2,000 grams. They told us what S is, 4.19. And that's going to be joules divided by degrees Celsius times grams. And our final term, delta T, it's the difference between 25 and 53.1, so that's 28.1 degrees. If you notice, we've got degrees Celsius that are going to cancel out in the unit for delta S and on that term on the right. Grams are also going to be canceled out, so what we're going to be left with is joules. That's our unit for Q. And now we just have to multiply everything together. So in this case, Q is going to be equal to 234,916 joules. That's a big number. It's perfectly okay to convert that unit to kilojoules, and we would just round it to 234.9 kilojoules. Both answers would be acceptable. One important thing to remember when using this equation, we're always working from the point of view of the system. So that means that since the temperature of the water went up, water being the surroundings, this is actually a negative change. So we would actually have to make this value a negative. The system lost this much energy to cause the surroundings, the water, to go from 25 to 53.1 degrees. If it was endothermic, we would leave the value as a positive. If the system absorbed an amount of energy from the surroundings. But since energy went from the system to the surroundings, that means the system lost it, so it needs to be negative. This is only a positive number when the system is gaining that energy, like in an endothermic reaction. Your question for this section: 1.6 grams of ammonium nitrate is mixed with 75 grams of water at 25 degrees Celsius. After the salt dissolves, the final temperature of the contents of the calorimeter are 23.34 degrees Celsius. Calculate the enthalpy change, assuming the solution has a specific heat capacity of 4.18 joules per gram Celsius and no heat is lost to the calorimeter.